you're very welcome here at the GSSI, although for the time being in a virtual manner. But as I told you, we're really keen to invite you in presence too very soon. So we hope that you will be able to have you in presence maybe next year, who knows. For those of you that do not know Tom yet, a few words of presentation. Tom is professor in regional innovation at the University of Stavanger Business School in Norway, where some of us have been for the famous GeoInno before everything exploded. If someone has his mic on, please turn it off. Okay. So yeah, I was telling about Stavanger, where some of us have been actually for that conference. It's not a fantastic place. He's also associated to the Center of Regional Innovation Economics, University of Bremen in Germany. His research interests are very much aligned with our own and with the fields of our PhD students, because Tom is an expert in the geography of innovation, with a special interest for knowledge networks and proximity with knowledge networks. His paper on JAG 2012 on proximity paradox is a must read, and I think that everybody here has read it at least once. He has also worked on the effect and evaluation of R&D policy at the regional level, on regional innovation systems. He has also worked on other topics of our research track, like renewable energies and tourism. So we are perfectly aligned, and I think that I mean, there's a very nice matching between your own interest, Tom, and our own. Okay. Tom is really has a terrific records of publications. Is really a great scholar, and we are very pleased to have him here for this presentation and for his paper on the diffusion of complex innovation. Now, let's just remind to everybody that the webinar is going to be recorded. Okay. So if someone does not want to be recorded, he has got an alternative. He or she can leave the Zoom and go and hear the webinar in our YouTube channel, where we're going to broadcasting the webinar. Okay. Having said that, rules of the game are as usual. First, Tom, we're going to go for his presentation, roughly 1 hour, and then we're going to have our standard discussion. Having said that, I'm very pleased to leave the virtual floor to Tom. Tom, please, the floor is yours.
Yeah, thank you, Leandro. Thank you for these very, very kind words, and also for reminding me for how long I'm already in the game. Of course, when you said this JAG paper, it is already a while ago, but yes, I remember it. So today, I would like to talk about something I have not talked that much about before. So let me share the presentation first, which is now, of course, gone, even though we practiced everything in advance. So let me just briefly. There we go. There we go. So hopefully you do see my full screen now, right? Sandro, I can't hear you.
Yes,
we see your desktop, however.
That's interesting, because beforehand, actually it worked. So that's
try again. So okay, now it seems to work. Now it seems that we have your full screen, but
no, only the presenter display. What on earth is that? This is really. Why is it not?
I don't know whether we can do something to help you.
No, give me a second. Just maybe entertain the crowd for
yeah, I will entertain the crowd. So I was just referring to that paper because it's very much well known. But of course, Tom has very, very, very interesting recent papers, right? So I didn't want actually to refer just to that paper. So the gallery of papers that Tom has is as much as interesting as the papers on JAG, which I just mentioned because it's one of the most quoted. But now we can see the presentation. I think you just need to put a sort of full screen, Tom.
Actually, it is on my side.
Is it? So we have it now, and
yeah, I see. This is fantastic.
We can see it. However, I don't know whether.
Okay, then let's try something else here.
So
let's try something else. I have to move on. We don't have. Now my sharing button is gone here. This is a nightmare right now.
Okay, I'm gonna keep on entertaining people. So I'll just to remind you the attendees that the Tom seminar is a virtual one, but next week, Wednesday the 3rd, we are going to have a real seminar in presence, okay, here in L'Aquila. So those of you who are in L'Aquila will be very much welcome. And then we're going to have, if I remember well, another seminar in presence, let me see, on the 17th of November. So the 3rd of November will be Federica Daniele from the Bank of Italy. Then on Wednesday, the 10th of November, we're going to have another virtual seminar by Juan Gabriel Brida. And then, as I told you, on the 17th of November, we're going to have a real seminar in presence with Lorenzo Zirulia from the University of Milan. Now I think we get it. Okay, Tom, I'm going to stop.
Well, thank you so much. I'm so sorry for that. Again, it's strange. It worked perfectly in the trial, and then it does not right now, or did not. So at least, but now you can see it. So as I mentioned before, the topic I would like to talk about is the spatial diffusion of simple and complex technologies. And it is a topic I haven't talked that much about before. That is, I haven't talked that much about the spatial diffusion part of it. Of course, I did some presentation and I did some work on the complexity of technologies, which I will also discuss subsequently. But let's start with a little bit more of a motivation. I think many of you have seen this figure, and I'm a little bit sorry, the picture is a little bit blurred on my side, but the point is that we have observed, or we know that knowledge is very, very unequally distributed in space. So we have places where knowledge is seemingly abundantly available. So where you have, and how does knowledge actually show in reality? You have experts, you have skills, you have capabilities in places which are just so different and so much more, and also so much more informative than you do have it in a variety of other places. So we have this very unequal distribution of knowledge. Of course, we do see that large cities tend to have more knowledge, that is more skills available, more experts on certain subjects being present in those locations than, of course, in rural areas. But as the wonderful map by a friend of mine, Pierre-Alex Balland and his colleagues, very nicely shows for the US, the distribution of knowledge is not identical to the distribution of population. Look, for instance, at this the most spiky place here, which is San Jose, Santa Clara, which is, of course, a representation of the Silicon Valley. While it does have a very high population density, it is by no means the largest population agglomeration in the US. So there are very, very interesting differences. And the question is, of course, well, why is that the case, and what type of implications does it have? And we know that this really matters because knowledge and technologies, or skills, expertise in technologies, well, they have been known for long to be a key driver or key drivers of economic growth. So this is one of our most fundamental thing we care about, in particular in innovation studies, in particular in innovation economics and regional science, as well as economic geography, for instance. And if we look at the contemporary literature, we do, of course, see a lot of work that particularly emphasizes that knowledge is of relevance for economic growth. And in particularly, it looks at the creation of knowledge. So we have a very strong focus, at least from my perspective, and I'm keen on hearing your perspective later on, whether I'm wrong in that respect or not. But what we hear, what we see in the literature is that a lot of studies really focus on where do new technologies emerge. So where are the inventors that come up with these great ideas and these new technological revolutions? Where do these breakthrough innovations or incremental innovations, both of them are important in certain contexts, where does that happen? So we have a very strong focus and interest also in the location of the creation of knowledge. And of course, this makes quite a lot of sense, because if you are located in a place or if you are close to somebody who has made a great innovation, that may be very, very helpful for your own economic success. So obviously, if you know inventors, if you are an inventor, this will have strong economic benefits because you can exploit this innovation, and it also signals at the same time that you do have expertise and skills that maybe others do not. So in particular, this first mover advantage comes to mind in this place. However, the question is, does innovation only benefit the inventor? So is only the inventor the one who benefits from an invention, meaning in particular economic benefits? And of course, the answer is no. There are also other economic actors that may receive benefits from innovations, which they have not done by themselves, but for instance, which they have adopted, have learned about, which they have incorporated into their own activities. And one of the reasons for why that's the case, so why it's not only the inventor who obtains or who profits from the potential benefits of an innovation, is that there's a striking difference between something being new to the world. That is the first time, let's say, a technological innovation has been translated into a marketable product, the first time that somebody has come up with a new service idea or something like that, which of course is new to the world, and that is great. And that has, of course, a lot of potential benefits for that individual. However, in many, many instances, or in a lot of instances, new to the world is one thing, but what really matters is something being new to a place or to a specific market. Even in the age of the internet, it is quite unlikely that one economic actor or an inventor will be able to serve with his or her innovation the entire globe, right? So in particular, when we think in geographical aspects, it is not possible usually to have one innovation out there and everybody around the world uses that and uses it in the way that the inventor envisioned it or in the way the inventor provides access to it. In some cases, we might actually observe that, in particular, if we think about social networks and virtual goods on the internet, there we might have the possibility of inventors to serve basically the total global market. But even then, the inventor will not be able to serve all the sub-markets where the product with slight adaptations can be put into use. And this is usually done by other actors who have learned about the innovation, who understand it, who are able to make it work, to adapt it, to slightly modify it, and then serve these distinct markets, either in a geographical sense, but also in a technological sense, in a market sense, that you find certain market niches with which you serve these products. And in that case, of course, also these inventors or adopters, let's put it like that, they're not really the original inventors to make this distinction. So these adopters will greatly benefit from that innovation because they obtain, so to speak, some kind of knowledge from the original inventor and which they put into use and generate economic benefits from that. So in particular, if we think about incremental modifications of some kind of initial original inventions that are adapted to specific contexts, you can make a lot of money or can be quite economically successful. Think about the very idea of social networks, which per se seem to be, you just need one social network, right? So one social network could serve the entire globe. And I believe many people at Facebook in particular really believe that idea. However, why then do we have so many different versions? Why do we have Twitter? Why do we have LinkedIn and so on and so forth? because they serve specific markets, specific segments of the social media market, which cannot be served by the original product, where they have made some adjustments, some modifications to the original idea, and of course, then make quite a fortune out of that. And by no means I meant that Facebook invented the social network, right? That was just an example. So also from economics theory, we know that being the first in something is good. So there are certain first mover advantages. You basically have a monopoly, which you can exploit and get economic rents from that. But there are also quite substantial second mover advantages. So then you already can learn from, for instance, negative experiences the first mover has made. You already benefit from some learned curve effects and so on and so forth. So you can build on something, and in particular, you know whether the thing works. So you may be able to restrict the risks associated with doing something or engaging with a certain product. And by learning about new innovations, you also expand your own capabilities. You build your own absorptive capacity, which will help you to learn or to invent in the future as well. So clearly, the benefits of innovation are not restricted to the inventor himself. There is also this entire debate about knowledge or innovation being a public good that is quite related to it. But I think this makes already clear what the entire idea is about. It's not only the inventor matters. It's not only the inventor who is able to benefit from certain innovations. So innovation is also beneficial, in particular, to early adopters. And what I a little bit hinted at, but didn't really make that clear on the slide here, is that I'm going to focus on not on the benefits on the consumer side. Right? So of course, innovations, in addition to the to benefits to the inventors or advantages to the inventor, have of course also a lot of potential benefits and advantages on the consumer side. But let's leave that aside. Let's rather focus on the supply side, which we actually do too frequently in our type of field, but that's a different debate for now. So even other suppliers of products, of services, may benefit from inventions that they have not come up with, but which they have adopted. And if we look at this idea where the adoption of innovation, in particular from a spatial perspective, has been studied, we do find that there are quite a number of literature strands that have engaged with this topic. So that have started to think about, okay, how does the adoption process, that is, some economic actor learning from another economic actor or from the inventor about an innovation and incorporates that into his or her own doing, and then maybe even diffuse it further. So this entire idea of the diffusion of innovation, which I assume you are very familiar with, has of course been at the core of, let's say, our general geography of innovation, if I may say so, literature for long. However, within this literature and intersecting with it, there are a couple of literature streams I just want to mention. So we have the traditional, let's say, literature on the diffusion of innovation. And there, these works go back in particular to the work of Rogers, Hagerstrand, which is a nice thing here because I'm actually right now in an office of a former PhD student of Thorsten Hagerstrand. Funny side fact, which no additional benefits on your side, but at least it's a nice story to tell. So these people have looked at how technologies, how specific products diffused in space and time, who was adopting it, and in particularly we're interested in what are certain characteristics individuals have that are early adopters, and I will talk about that a little bit more in later. The second literature stream, which for sure you're also all knowledgeable about, is what I would call the knowledge spillover literature. So here in particular, the focus was on a geographical perspective. That is, the idea was, to what extent does a specific location grants you access to knowledge, for instance, by being closely on close proximity, geographic proximity to specific knowledge sources. So for instance, do you benefit from, as a firm, being in a region, being close by a university, let's say. In that case, there might be certain spillovers via mobility patterns, via just observational learning, different types of collaborations that may exist there, unintentional knowledge transfers, and so on. So the idea was here, so to what extent does being in the right place gives you access to knowledge, gives you access to innovation potentials, to new products and services, which you can incorporate into your own activities. And usually a kind of knowledge production framework is employed in this type of literature, in which the spillover potential is used as an additional input factor, right? You look at your own inputs in terms of expertise and knowledge. What do you generate from that output, innovations, knowledge, and so on and so forth? And you consider, okay, do I actually have, at least on paper, so to speak, access to these nearby knowledge sources? The third literature, as more recently, and of course should have also been in bold, the term relatedness, that is, it expanded the idea of these knowledge spillovers by saying, well, it is not just geographic proximity that matters. So it does not only matter that you're geographically close to, for instance, a knowledge source, to an inventor who came up with an idea, but other proximities matter as well. And in particular, technological proximity, which basically describes to what extent do you actually have the absorptive capacity to understand, to learn about, and to utilize an innovation or new piece of knowledge. Last but certainly not least, the literature stream I also would like to mention, and which Sandro has mentioned in the introduction as well, are knowledge networks. Here, the idea was very much inspired by these other types of literature streams I mentioned before, that, well, maybe it is possible to really look at interaction patterns between economic agents. And now I have to do a small dance move to turn back my light on here. Don't ask. So infrastructure is a weird thing. So in this literature, people have thought about, okay, how does knowledge actually get, and knowledge includes information about new innovations, new products, new services, how does it actually get transferred from one economic actor to another one? And couldn't we do more to understand this process than just looking at the geographic or technological proximity between them, but really look at how do they interact? And that gave rise, so to speak, this idea to the idea of knowledge networks, which I'm not going to discuss further here today, but there I could give an entire presentation on that topic. I will not. So if we look into this literature stream, then I think in particular, for my presentation at least, but also as a general message already for this entire presentation, there are very important insights of the early innovation or traditional innovation diffusion literature, which I may say has been put a little bit to the side. So I don't see that many references to it. I don't see too many scholars engaging really with this traditional Rogers-Hagerstrand type of innovation diffusion literature these days. However, it holds very important messages. In particular, that in much of our contemporary research, and I'm looking at you, relatedness or related diversification literature, which I'm part of myself, we again treat spatial units as kind of independent containers. That is, we don't care so much about what's happening inside a region. We don't really look at how a region is connected to or maybe in the neighborhood of other regions. We predominantly think about, okay, what type of knowledge in what structure is it related to what I'm looking at is present in a region, and does that impact diversification of this region, of economic actors in this region in the future. So there is this tradition to basically treat regions as containers, relatively isolated from each other. Sometimes at least we add some tests for autocorrelation to not make this too explicit. Also, in addition to considering more actually how interactions and how things that happen in one place may be important for the development of another place, another dimension that I find a little bit underdeveloped and underused in our type of literature is the time dimension. So quite frequently, we just compare t-1 to t. What has happened, if anything? But of course, there are quite distinct dimensions, quite distinct processes that work along the time dimension. Some processes are much slower than others. Also, the sequence of events may be really important in this context. We don't engage with that too much. And if we think about looking at different technologies and localities or places, then we sometimes have the habit of looking at the average. So we are ignoring a little bit about the heterogeneity between technologies and between localities. And at least with respect to one of the last points I mentioned, this heterogeneity in the terms of technologies, in terms of where they are located, where they're invented, how do they diffuse, what type of impact they have. I think we're engaging with a very interesting topic here, which I would like to highlight with this wonderful plot, also by Pierre-Alexander Balland and co-authors, that basically look at or make a distinction between complex and simple technologies. So they argue some technologies or even some economic sectors by that token, they are more complex. The underlying processes are more complex, implying that it is much more efforts are required in order to have an expertise to be able to really produce products or provide services in that field that are competitive. So it takes much more to become an expert and to be successful in these fields. It is much harder to understand these fields. You have to invest more resources and so on and so forth, which is captured by this complexity dimension. And what they found is that if we categorize technologies by different degrees of technology, and then look where they are located, we actually find many of these technologies to concentrate in particular in urban places, that is, in places with high population density or high absolute population. And then again, the question is, where is this coming from? So not only in the initial plot I've shown you, there's a total number of innovation, let's say the pure quantity of innovations, at least as represented by patents, seems to concentrate in cities. Why is it even more so in many cases for the most complex pieces of knowledge, the most complex technologies? A small spoiler alert here. This is crucial because complex technologies are also the ones who most likely generate the highest economic returns, meaning that we see an even stronger advantage to being located in urban regions and large metropolitan areas, because there you have these complex technologies, you have experts, you have capabilities in these complex technologies that offer the highest economic rewards. And we see an increasing imbalance between these urban regions and the peripheral regions. So that is more or less the motivation. We have a lot of research on the diffusion of innovation in different perspectives. We care about who learns what from whom, but we also know there's a lot of heterogeneity, and one crucial set of heterogeneity here is with respect to technologies, for instance, along the complexity dimension. So let's talk a little bit more about the ideas of the diffusion of technologies here. If we look at the traditional adaptation or diffusion literature, in particular inspired by the work of Rogers, who I really recommend you to look at if you haven't done so, they argue that the degree to which, or the way in which innovations, new products, new services, new technologies diffuse in a social system, independent of space, just a social system, basically is driven by a number of characteristics of the innovation itself. What are requirements? What is its usefulness? Usually, the more useful innovations tend to diffuse quicker, for instance. The type of communication channels matter. So how efficient is the communication, the diffusion of the information about new technologies in that social system? This literature is also very, very much interested in characteristics of adopters. So who are the ones, apart from the innovator, that actually adopt a new innovation, that are the first who try out new products, who experience new services, and actually are very, very crucial for the later success of that technology, innovation, and product. Because if the early adopters say, well, this is not working, I'm not really convinced by it, well, basically the innovation will fail. And you see this, for instance, nowadays with all these reviews, these review influencer channels also on the different social medias that basically test and try new products and services, call a verdict on it, and then that has an impact on the diffusion or the success of this product subsequently. Also, research in this tradition talks about the way the social system works. Are there certain support measures for new innovations? How well are generally new things accepted in societies? And a very crucial point, the time. What this literature already noticed is products diffuse at different speeds in the social system. Different speed meaning it takes different times for a certain share of the population to adopt a new product or a new service. And there's, of course, this very famous diffusion S-curve, which has been confirmed basically for every technology or every product you look at. That is, early on, you have a kind of exponential growth, more and more adopters follow in line and make use of this product or innovation. And then subsequently, you have the saturation. And of course, there's not too much, not additional adopters left or consumers left that actually adopt this product. So we have this general S-curve diffusion pattern. However, and this is a very, very recommendable study by Pizzoni, there is substantial variation in the diffusion speed between technologies. And this is now interesting. I alluded to that already a little bit before. Diffusion speed, is this just something, well, we don't really care about? We just know, okay, some technologies may diffuse slower in social systems, others are not. Well, as soon as we realize that being able to use a certain technology may make hell of a difference in when we can benefit from its economic returns or when we can extract the economic returns, diffusion speed matters a lot. And I think in these times of the pandemic, we have a very, very clear example for that. Of course, it mattered how quickly the diffusion of vaccinations, for instance, or of the underlying technologies took place, because that very much impacted how quickly societies, economies could get back to a normal life. So that's just one example. Of course, if you think about other technologies, you will find similar ones. But what we know from this literature, well, it differs. The diffusion speed of technology differs. And another thing that we learned from this literature is very much related to the idea of Hagerstrand, who said, okay, we now know a little bit about the time dimension. So technologies differ in the way they diffuse in the social system. However, he also observed that, well, there are different spatial patterns to these diffusion processes. So it matters in terms of where are you located, in terms of when do you get to know about an innovation and when you're ready to use it. So your location has an impact on the likelihood and the time it takes for you to know, to learn about an innovation, to be able to actually implement a technology and to benefit from its economic returns. And he observed two, and later research identified a third type of diffusion pattern. So in the first one, which is here listed as second, but is the easiest to understand, it's a so-called contagious diffusion. Some products, some technologies, some innovation diffuse simply along the geographic dimension. That is, you have a certain place where an innovation takes place, and from there it diffuses in kind of waves through space, right? So places that are close to this original hotspot or this the place of invention benefit the earliest or learn about it the earliest, and from there it diffuses further in space. But that's not all. There was a second pattern he observed, and that's what's called hierarchical diffusion. That is, certain technologies, certain products also originate in one place, but then actually diffuse first to other central locations, usually metropolises, but not necessarily, urban places, very central locations that that were the first ones to learn about these innovations. And from there, it either continued to diffuse down the line of the urban hierarchy, or went on to a contagious diffusion pattern. And a very good example of that is closing styles, which usually emerge in very urban centers, which then are quickly adopted around the world in the bigger cities. And then it tends to take some time before the more peripheral places actually adopt this way of style, let's say. And we have also observed something, in particular later research showed that there's something like a leap-like diffusion. So there doesn't seem to be a particular geographical pattern to the diffusion of product and innovation, at least not a geographical pattern. If you consider other dimensions, I'll talk about that one later, you actually may find that, well, this leap-like diffusion pattern, of course, has a systematic pattern, but it's just not spatial in nature. So, and now let me bring this all together. I argued before that we in our literature have an increased interest in the complexity of technologies, of economic sectors, because we know that complex technologies and economic sectors tend to be the ones who generate the largest economic benefits. So we want to be the ones exploiting them, and actually considering the ideas of the diffusion literature, we want to be the first ones, or at least as early as possible, to learn about a new complex innovation, to be able to exploit it, to implement it into our own processes of production and services. So complex technologies tend to be the ones we're most interested in. And now the question is, okay, do they actually have a distinct spatial diffusion pattern? So what does the literature tell us about that one? Well, Balland and Rigby find for complex technologies to diffuse slower across larger geographical distances, which would suggest that probably they diffuse in a contagious pattern from the place of invention to, firstly, to nearby regions. Again, let me wander around here to turn back on the light. To nearby regions, to nearby places, and then from there onwards across the space. However, they also find in later research, or at least Alex find also, and some of my work also confirms that complexity or complex technologies and sectors tend to concentrate in large cities. So if they are primarily located in large cities and not so much in the places between them, maybe it is rather a hierarchical diffusion pattern. Or if we really dig deeper into the proximity relatedness literature, they argue that space is great and should be considered, but actually there are other dimensions, in particular the technological relatedness dimension, that may be important. That is, if you have the necessary absorptive capacity, the necessary skills to learn and utilize complex products and technologies, that's what makes a decision about when you adopt it and how early you will adopt it. And that would actually suggest maybe we don't see any particular pattern from a pure spatial perspective, but rather have this type of leap-like diffusion pattern, then at least if we look at the map. So we have these three distinct hypotheses or ideas, at least, coming from this literature. And what I would like to do next and subsequently for the rest of this presentation is, let's test this. Let's get some insights. And the question is, why would we be interested in that? Well, again, if complex technologies or complex products are the ones that bring economic benefits, it is quite important to know who will be the first one exploiting it, not only the inventor, but who will be the next adopter. And does it benefit particular places first, or maybe even longer or at all, and not other places? So from a geographical perspective, it's really interesting to understand that. So let me move over to an empirical study that puts these ideas to a test. And first, we need some kind of empirical data. And here I have to disappoint you. We are just relying on very, very standard data, and that is patent data. So in particular, if you want to study long time diffusion patterns, there's not many alternatives, even though Rogers and Hagerstrand, for instance, collected some very fascinating work on product adoption and product sales. So there are alternatives. we relied on the stuff we knew best, and that is patent data, and created some kind of variables from it, which I'll talk about subsequently. So we look at the US because there we have this fantastic patent data data set, HISPAT as well as NBER data, patent data that we combine into a consistent data set covering the period 1836 to 2010. We are also able, and of course, this is quite standard, to distinguish between different technologies. Here we follow existing approaches and we say, well, we look at 655 distinct technologies, which in this case are identified by 4-digit CPC, corporate patent classification classes, similar to the IPC, but with a very important difference we can talk about more about later. We then constructed 10-year time periods because for these times in the 19th century in particular, there is no annual data available for some of the control variables we need, most importantly, population. We focus on metropolitan statistical areas, which is also quite common. However, then we have to make some of those tough empirical sacrifices sometimes you have to make, because we would like to study comparable technologies. We wanted to study technologies that actually diffuse in space and actually had the chance to diffuse in space. So we decided to look at 100 years. We looked at technologies that existed in 1836 that were at least present in one region, and from there diffused over the next 100 years. We decided not to include technologies that emerged later than that, because then a lot of systematic differences might occur, biases might occur because different communication technologies were available, and so on and so forth. So we wanted to have a comparable set of technologies. And we said, okay, let's look at these technologies that actually diffuse in space. So it's not really useful to study diffusion patterns of technologies that are just adopted by 1 or 2 regions, but rather we said as a minimum 50 metropolitan statistical areas need to have adopted this type of technology. Adoption in this case means have at least one patent in this technology that's associated to these technology class in any of the years subsequent to the time period I'm looking at. So at least 50 MSA. We can discuss about all this. Truly, there are some arbitrarities. It is a little bit arbitrary, of course, these thresholds, but they worked out fine in our case, and there are some reasons for that. So if we look at the histogram of the number of CPC classes when they have been introduced in this time period, we see that most of them start really early in the 1830s and 1840s, and subsequently we have fewer CPC classes that are really new to the system. So that makes us quite comfortable to look at the very comparable setup here. An example of a diffusion pattern, which is just something that is, I would say, is a perfect illustration of that. If we look at the cutting edge technology at the time, vehicles drawn by animals, which I think you can imagine, how it diffused, we clearly see that it emerged at the East Coast, where it was invented near to, if I'm not totally mistaken, near to New York City, but not directly in New York City. And from there diffused kind of contagious, at least it looks like, to New England as also a little bit to the south. And then in particular was quite quickly adopted in the Detroit area. Why do I mention Detroit explicitly? Well, some of you may know that one of the biggest car companies in the world, GM, was founded by somebody who actually had a business in the vehicles drawn by animals industry. So there you see why we selected also this type of example. As Germans, we're always quite interested in car manufacturing and the car industry. So this is a predecessor to that one. So
sorry,
here we see,
Tom, can I ask you something?
Absolutely.
Basically, a color gets switch on when a pattern in that technology is filled. Is that the ratio of adoption?
No, basically it's the time, the first patent, and that with an inventor from that region is registered.
Okay, good.
right? So if you look here at Dallas, I think that was about between 60 and 80 years after the first patent in that patent class. Okay, so, and of course, we love maps. I'm open to admit that. We really love maps, but we also need to put a little bit more substance to it. So we really need to build up some kind of an statistical approach, testing whether we observe certain diffusion patterns. Our dependent variable is the time it takes until a particular CPC class, that is a technology, is adopted by a region. That is the first time a patent associated with this technology class is registered by an inventor residing in a particular location. And then we have two core explanatory variables. The first one is the geographic distance to the inventor region. So that is the location of the first patent associated to the CPC class or technology, and the geographic distance to the closest adopter region at the time. So if I see an emergence, I see a patent, let's say in a particular class coming up in Dallas in, let's say, 1860, what is the distance to the next region, or what is the closest region that has already adopted, that is, that had already a patent in this class in the previous years, right? Two very simple, I would say, variables, but as I will argue now, quite powerful. We then have a couple of controls, which I'll come back later as well when presenting the findings. Population, we construct also technological distance, which is all fairly standard. We also look at social distance. So when we see, where we look at the co-invention of patents in general with inventors from two distinct regions. This is a little bit less interesting, so I'll skip over that one quite quickly. The third core element of our exercise is, of course, the complexity of technologies. So we need to have a kind of measure or an idea what constitutes a complex technology and a simple technology. And here we draw on an idea which we developed some time ago. We see that technologies, or we argue that technologies can be perceived as networks or combinatorial networks of individual components. That is, each technology consists of different elements or knowledge components, and they are combined in order to make a technology. Think of a car, for instance, where you combine the knowledge component of wheels with the one of a steering wheel, or of a club, or of seats, and so on, with an engine, and so on and so forth. So if you have these individual components, they are connected, combined in a certain way. In terms of patents, we look at, in particular, how individual 10-digit CPC classes, part of the same 4-digit CPC class, are combined on patents, co-occur on patents. I'll show you an example in a second. And then we look at how diverse are these structures of how these knowledge components are combined. So think of a technology in which we have 4 central components, and there are a lot of subcomponents that are directly linked to that one. So there's one integrative component that always integrates different subcomponents. Well, if a technology is structured like this is actually quite simple, because then all you need to know in order to describe this technology, for instance, is what are the central components and which components connect to it. That's all you need to know. If you think of a technology that actually shows different combinatorial patterns, things become really more complex until you end up into something that is close to random, but of course not fully random, where in order to describe this technology, you really need to know all the individual components, and you also need to know with which other components are they combined. There's no organizing pattern. And I call this structural diversity. I talked about this one in other presentations, so I'm happy to talk more about it after the talk. Let me just say, by using this approach, we can actually get a measure of complexity at the level of technologies, that is 4-digit CPC classes. This measure has been confirmed in a number of papers by now, and it works really well. We also have to pay credit to Emert, Streib, and Demer, who invented a kind of network diversity score that allows us actually to capture empirically this concept of structural diversity. For now, all I would like to say is that diversity in the ordering principles, in network science, we call this topologies, in these combinatorial networks of technologies, gives us a measure of complexity that we call structural diversity. So we can do, with this measure at hand, we can differentiate technologies according whether they're simple or complex. Actually, it's a contagious measure, so we know which technology is a bit more complex than another one and by how much. We do have our dependent variable, the time it takes before a region adopts a certain technology. We have these two distance variables in particular that will help us explain what was going on between 1836 and 1936 in terms of diffusion of technologies. What type of empirical method we're using? We use a survival analysis, which is particularly designed to describe the time it takes, which is a very particular dependent variable as there is censoring in place, for instance. So we use this type of survival analysis. We can also talk about that one later if you want. We adopt here a very recent approach, which is called Bayesian spatial survival analysis models, which allow us to consider also spatial dependencies to a certain degree in the explanation of these diffusion patterns. So what we do, take you very slowly through that one. For each of our technologies, remember 271, we run an individual spatial survival model. This gives us an idea about variables that impacted or that explain the time it took for a particular place to adopt a technology. I'll put more generally, it explains the time it takes for the adoption of these technologies across space. So for instance, if we find our distance variable to the inventor variable to be significant in this scenario, it means if we have a positive significant coefficient, for instance, it means that a larger distance to the inventor region will have a positive effect on the likelihood that a technology is adopted, which is not really what we would expect, but just to make a case in point. So we run 271 of these individual survival models, which gives us coefficients for each technology, for each of these variables. And then we apply something called meta-regression, where actually the coefficients of these 271 individual regressions serve as units of observation in our regression analysis. So then we wonder about why do these coefficients differ between technologies? And this variance in the coefficients is then explained in particular with our complexity variable, because we have this complexity variable for each individual technology, but it doesn't really make sense to make this time variant, because at least for this time period, there was not too much change in the complexity of these individual technologies. So it rather makes sense to look at, do we observe different types of coefficients? Do we observe larger, smaller, positive, negative coefficients, for instance, for this geographic distance variable, when we consider different degrees of complexity at the technology level? And we do this in two forms. First, we look at only models, diffusion models that included the spatial variables, the distance variables. And then we do the same thing by looking at models, spatial survival models, where we include the full set of explanatory variables, because that will also give us a distinct insight. We can talk about this again after the presentation some more if you're interested in the specificities, but I think the general idea became quite clear. So let me come then to the results. The first one, does technological complexity imply a specific diffusion pattern? That is, do complex technologies diffuse from a spatial perspective in a different way than simple ones? To make this clearer, we summarize the results the following. We have our two variables, distance to the nearest adopter region, distance to the region of invention. For each of these two variables, we get a coefficient from our spatial diffusion pattern, diffusion models. which we then can, because we have two coordinates, put into this very nice matrix. And the idea is that different positions in this matrix represent different types of diffusion patterns. Let's say if the distance to the nearest adopter region has a negative significant influence on the likelihood of adoption, and the same is true for the distance to the region of invention, this most likely will represent a contagious diffusion pattern. That is, distance is all that matters. Being close to the inventor region, being close to the first adopter region is what defines your likelihood of adopting a certain technology. In contrast, when we have a positive effect, or at least a less negative effect of the distance to the invention region, so that is actually the likelihood that you adopt a technology increases with the distance to the invention region, but may still be negatively influenced by the distance to the nearest adopter region, then we rather suspect a hierarchical pattern, because that means the technology has first diffused to another place, and then from there downward along the geographical hierarchy of places. Large leaps and small leaps are the two resulting scenarios, which are a little bit of less interest to us at this stage. So we're particularly interested in these two scenarios, which Hegerstrand already put forward. So here's the result. Each of these dots represents the two coefficients we obtain with respect to these two variables in our diffusion models. So if, for instance, we look at quadrant 1, the one with the red 1 here, and we see there a dot, it means that the distance to the nearest adopter region obtained a negative coefficient. Also, the distance to the region of invention had a negative coefficient in that diffusion model, representing one technology. And if the dot is dark blue, it means both of them have been significant. So again, one dot, let's say the one closest to the left lower corner, represents a technology, and it represents the two coefficients we have obtained in our diffusion model for this technology, the coefficient for the distance to the nearest adopter region and the distance to the region of invention. And if we see the dot being located basically in this lower quadrant, in the quadrant 1, that is characterized by negative values of the coefficient of the distance to the region of invention, and the negative value in the coefficient for the distance to nearest adopter region, that corresponds to a contagious diffusion pattern. And we see that for most technologies, this seems to be the case. Some also show a hierarchical diffusion pattern, some something that we would call small leaps, and hardly any really falls into this category of large leaps, and in particular, none really falls significantly into this field, because there you see the 3 dots in the upper right quadrant are just grayish. So our first indication is that our first result is that most technologies their diffusion is rather described by a contagious diffusion pattern, that is, geographic distance matters. But now we employ a more explicit test, this meta-regression, that explains, so to speak, precisely the location of these dots. So we have 4 scenarios. Either the dot is in the in quadrant 1, 2, 3, or 4. So we explain the position in these 2x2 matrices by considering the complexity of each technology represented by these dots. And what we find is that complex technologies are significantly less likely to fall into the quadrant 1. So they are actually less likely to show a contagious diffusion pattern. We do find, however, some indication for that these complex technologies are more likely to show a hierarchical diffusion pattern. So they're more likely close to or even within quadrant 2, which is interesting because it tells us we can confirm kind of our first hypothesis. Complexity does seem to have a significant relation with diffusion patterns. By that, it makes it less likely to have contagious diffusion and more likely to observe a hierarchical diffusion. But then we would like to know a little bit more about the other control variables, and it will become clear to you in a second why this is important. So are there certain explanatory variables impacted by complexity, or is their impact conditional on the degree of technological complexity? Again, we run our first stage survival regression with all explanatory variables, and then we, in the second stage, run meta regressions explaining these coefficients with the explanatory variable complexity. What we find is that complexity increases the effect, that is the coefficient size of technological distance. So that is, in this case, it's a little bit, the interpretation is more difficult, but it actually says that the closer you are in technological terms to the focal technology, that is, the more skills and competences you have in fields related to this focal technology, the more likely it is that you will adopt this technology, which makes, of course, a lot of sense. It is kind of, you need absorptive capacity. You need to be in this kind of related field to have heard about a certain technology to adopt it. And this is something we might say, well, that could explain actually why our results for the other type of diffusion patterns other than contagious were not that strongly, because it might suggest that we have this leap-like diffusion pattern in space, which is actually caused by technological distance. So it might actually be contagious in the technological dimension, so to speak. We don't find any effect of social proximity, which is quite interesting. We suspect that is because social proximity is also quite strongly correlated with a geographic proximity to the adopter region. Right, so the more people are active in related, in similar technologies close by, the more likely you will have co-invention taking place. So maybe that variable is capturing some of that effect. We find that complexity has a lower effect on population, meaning that actually this idea of hierarchical diffusion, which would suggest that the technology jumps, so to speak, in a diffusion process from the most central, that is most urbanized places with the largest population, and that explains its diffusion in space, is actually not that strong for complex technologies, or actually it's weaker for complex technologies. It is existent. So we still find a positive significant coefficient of population, but the coefficient tends to decrease in terms of effect, in terms of explanation of the time it takes of adoption when for complex technologies. So apparently this hierarchical diffusion pattern or leap-like diffusion pattern is not really related to population, but again, probably much more to the technology dimension. We find that complexity has a stronger effect on diversity, meaning if you are located in a region that has a set of very diverse technological skills or expertise in a diverse set of skills, it's more likely that you will adopt a technology earlier than later. Wrapping this up, because time is up, and I'm sorry I'm already a little bit over time, but that was because of the technical difficulties in the beginning. So hopefully Sandro grants me another 2-3 minutes. Thanks a lot. Coming to the conclusion, as I mentioned, much of the geography of innovation literature, and much is of course hard to quantify, but at least from my perspective, a lot of it focuses actually on the creation of innovation or the emergence of innovations. And we see, relatively speaking at least, less work that really looks at the diffusion and adoption of innovation, which however might be at least as insightful as other types, as the former type of studies. With respect to, and this is actually, there's something wrong on my slides, but with respect to the core insights of the empirical study, we showed that we have this long-term perspective on the diffusion of technologies in the study that is quite interesting, because diffusion tends to happen rather slow over time. So we have to take this long-term perspective, which has certain limitations, of course, in data availability in particular. We see that complexity is another factor that helps us understand distinct diffusion patterns. So while other research already has shown that complexity is important for, let's say, the economic benefits of technologies, that it's related to economic growth of regions, for instance. It is related to the diversification possibilities of countries and regions. With this study, we confirmed that it also matters for the diffusion of technologies. That is, complexity helps us understand in why certain technologies diffuse in a different way than other technologies. And we see that spatial diffusion is interesting, absolutely, but that, I think here went my mouse, okay, that, now something, okay. Whatever is happening today with my technology, I think now my presentation has updated from another device. So we have in this case that complexity is a very insightful dimension also for the diffusion pattern of technologies. And I think I covered already those core insights. I think that technological proximity is really one of the core dimensions we have to consider when we want to understand differences between diffusion patterns of technologies, not just the spatial one. Of course, there are interactions between the two. And we definitely need more studies that confirm or reject our ideas and our findings that should particularly use different geographical contexts, because as much of the work on these type of issues, we are a little bit biased towards the US, for which we have this very fantastic long-term data. But of course, other places are as least as, if not actually even more interesting to look at because of their distinctiveness. So with that, I really want to thank you for staying with me through this presentation. Thank you for your attention, and thank you for the invitation once more. And I'm really sorry for these technical difficulties, which I didn't expect to happen to someone who has been teaching through Zoom for almost 1.5 years now. Well, it's a complex technology.
Don't worry, Tom. They were pretty bearable. So I mean, they didn't really cause any price in terms of attention, at least to me. So you don't need to excuse them. It's fine. It happens. It happens. So thank you very much for this interesting presentation. I think that we should really appreciate also the efforts that you have done to grounding the paper, you know, in a wider debate and literature in terms of innovation diffusion. That was really helpful, I think, especially for our PhD students. Now, as usual, I will start by giving priority to our PhD students. Maybe we could start from a question that we got from the chat by Alessandro Cardelli. Maybe that you also, Tom, can see it. Who says that he wanted to know something more about the concept of survival and technology adoption diffusion. You could address that issue first, and then we'll see if we have questions from our attendees. Okay?
Yes. So thank you. That's always a thing that is quite interesting. We use certain terminologies that is absolutely clear to, for instance, to me, to the presenter. But of course, if you haven't worked with this particular type of, let's say, empirical models, this may sound strange to you. Why is it called survival analysis? Actually, a different name is event analysis. I think that's how it is more known in particular in economics. But it originates more or less from medicine and medical sciences, where the idea was to see, for instance, if you have a medication, you have a treatment, and you would like to know whether it had an impact. And what is, let's say, one of the most important impacts it should have, the time period it takes for somebody to still live. So basically, whether a treatment prolongs the ultimate end through this treatment. So whether somebody survives longer by receiving this treatment than by not receiving this treatment. So the time it takes until an event occurs. In that case, in medical, usually it had a bad connotation, this event. Let's say it could also be healing, then it's a positive one. But it originated really from testing whether treatment had an effect on the survival. And that means all you observe is the event, So, and how to explain an event? Well, you're not really interested in the event, but you're interested in the time it takes until the event takes place. And that is really the dependent variable in this type of analysis. And therefore, I still use this word survival analysis. Event analysis might be similarly correct. But if you, for instance, would like to run a similar regression in R, let's say, then you have to look for survival analysis. So therefore, it's probably good to know this term. Hopefully, I've answered your question.
Thank you. Thank you very much, Tom. I don't know whether Alessandro is happy. If not, just drop a line in the chat. I've seen that in the meantime, some cameras have switched on. I don't know whether this is so prodromal to questions. We have PhD students both working on proximity and complexity. So I don't know whether they want to raise question. If it is so, please just raise your hands and I will leave you the right to speak. Any question from the floor? Any question? So does Francesca Inami? Francesca, please go ahead.
Hi, can you hear me?
Yes, perfectly.
Thank you very much for the terrific presentation. For me, it was great and inspirational. And because I've worked on social proximity, I was curious about your hypothesis. It wasn't really clear why this relationship you found it like non-significant, and in terms of spatial terms, what was the hypothesis and what's your explanation for its not significance?
Yeah, perfect. Very good question. Where we got this inspiration from, I mean, yes, we've done work on proximities for some time now, so naturally we were also interested in other types of proximities. But actually, it is already an idea going back to Hegerstrand, and actually earlier than that already. The idea is how this knowledge about or information about a new product, a new technology, a new service, how is that communicated between individuals? Because in the end, we're talking human beings, and it's of course through social interaction. So he actually argued back then already that this contagious effect of innovation diffusion or product diffusion is to a certain degree due to social interaction patterns being very much correlated to geographic proximity. Definitely at the time period he studied it. So the idea was parts of the explanation for this negative effect of geographic distance on the diffusion of innovation is due to that it happens through social interaction, and that tends to be constrained by geographical space. And nowadays, and I have to be careful here because I'm not fully sure whether he already included that, but the hierarchical diffusion of innovation is, of course, also explainable through social interaction, because we know that interactions between urban regions, between highly central places, is more intense in a lot of instances than with respect to nearby regions. So actually geographic distance matters less. And there's this nice story about the Silicon Valley that has, due to all its migration, very strong relationships or individuals there to Tel Aviv, for instance, in Israel. And quite often it is a new technology and innovation taking place in Silicon Valley is, for instance, learned about earlier in Tel Aviv than in Los Angeles, which is geographically much closer, but because of this more intense social interactions there, it diffuses, or the information about it diffuses quicker along those lines. So we also could have expected that social proximity also explains this hierarchical diffusion pattern as well as a contagious diffusion pattern. Unfortunately, in our case, it turns out to be insignificant. The reason for that is most likely the following. Our event is the first patent in a certain technology in a region. So we cannot model social interactions with respect to that technology because it's not existent in that place. So we can, we basically summarize then or average across all technologies in a region. So any type of social link that may exist between an inventor in any type of technology in region A and region B. And of course, this is very general and not technology specific. So we might actually lose an important dimension to social interaction, and that is that context matters there as well, and the technological dimension as well. So very long answer to a short and precise question.
Thank you. Francesca, are you happy with that? Absolutely.
It makes all the sense now. Thank you very much.
Right. And now there's a question that I did expect from Andrea. And I suspect there's going to be a question about complexity. I'm sure about that. Andrea, please go ahead.
I can't hear you.
We can't hear you, Andrea. We can't hear you. Try again. Maybe you are muted or something.
Sorry, because I am in the open space. Thank you for the presentation. It was really interesting. Actually, I have many questions, but okay, I start with the Sandra was expecting. Yeah, because we are working with complexity too, and there are some applications that use like pattern data to as an instrument of complexity. The first question is what do you think about it, because I'm not sure about that. And the other question was related.
Can you repeat that question? I didn't fully understood it. Sorry.
Yeah, if you think that, because there are some scholars arguing that patent could be used as an instrument of complexity because it's inside, there is the technology content inside.
Okay.
And now the question that I was thinking also was related to what you mentioned about Silicon Valley. I was thinking if it is possible to include a non-patent knowledge. I don't know, for example, the presence of cluster or an industrial pole that capture, because for me it was strange that social proximity was significant. And the other was also related to that, if there are constraints for firms to patent that could affect the results. I don't know, thinking back, for example, on size, fund, also the previous experience, because if you know how to patent, maybe it's easy for you. These are the three questions. Thank you.
Okay, perfect. Very good. Let's see whether I remember all of them. I start with the first one. Can you actually extract information about the technology, the complexity of technologies from patent data? That's at least how I interpreted your question. I would say yes, to the degree that patents represent technologies. And that differs, of course, between technologies. We know that in certain fields, no patenting takes place. There's a striking difference, which I actually haven't really seen to be exploited. For instance, in Europe, it's really hard, if not impossible, to make patents on software. While in the US, it is. So technically, we can get a complexity information out of patent data for the US, but not Europe. So there are these kind of differences, and also between industries. In pharmaceuticals, we have 80–90% of all innovations are patented. In mechanical engineering, we're talking 30–40% or less than that. And there might be, again, certain sectors where patents don't play a role at all. So we have to take that into account. However, on the bright side, let's say, whenever we look at patent data, we look at something relatively comparable, because we automatically focus on something that has been patented. So even if it's in chemistry or in pharmaceuticals or mechanical engineering, it is similar in the respect that it was possible to get a patent for it. So therefore, we can at least, when we make this type of analysis, focus on or make interpretations with respect to innovations that are represented by patent data. So that's the first part answer of your question, that I believe, yes, we can use patent data. We just have to be a little bit careful about in what context and what is the general interpretation. The second thing is, how do we derive complexity information or information about the degree of complexity from patent data? Well, of course, I assume you're knowledgeable about the different approaches that are out there. Quite famously, of course, the Hidalgo-Hausmann approach, adopted by David Rigby and Pierre Alex, for instance. I put forward a measure, Sørensen and Fleming put forward different measures, and all of them have their strengths and weaknesses. For me, at least, a central thing is, well, I'm also coming a little bit from this regional science perspective and spatial econometrics. I don't want to have a dependent variable or an explanatory variable that is based on a spatial distribution of something. I'm just too worried about that there's some kind of a endogeneity quasi built-in. And that's a problem, so to speak, with the Hidalgo-Hausmann approach, which utilizes information on the spatial distribution or co-distribution of technologies, sectors, firms, whatever, and then builds a measure on that one. So apparently this measure represents some of these spatial features. And if I then use it actually to explain against spatial features, well, there might be a problem. I made in this paper also the argument that with the Fleming and Sørensen approach, there are some issues. And the one I propose seems to work. That being said, I think those are great ideas, but eventually, and you can see already research on that one, we will have to go to the text data, right? So this is text information that is contained in patent data, working with keywords, working with patterns, semantics, and so on and so forth. That's the way to go. I think we're just scratching the surface of the information that is actually contained in patent information by using these classifications. To a large degree, this has something to do with our limited capabilities, or at least mine. I don't want to include you, but at least my limited capabilities. So that's with respect to the first question. The second question, which of course I have totally forgotten about now, maybe it was whether we could include other types of variables into our models. Maybe it was the third one, I'm not sure. Well, the problem is, of course, we're looking at a time period 1836 to 1936. I'm quite comfortable that there was not a technopole existing or a cluster as we would define it today existing back in those days. I'm not entirely sure, at least not as a very common pattern. Back in those days at least, we're really talking mostly individual inventors, people that more or less by themselves did some R&D or something we would describe as R&D today. The professional R&D lab only emerged after the 1940s or something between the 1920s and 1940s. And that really changed the landscape, of course. So actually, we're quite happy to leave that period out because that might have induced different types of patterns. But of course, would be interesting to study it as well and see whether that makes a difference or not. But at least with the time period under study here, we're talking individual inventors working in not necessarily in isolation, but with limited interactions to other people in their places and rather in other places. Now you have to help me out. I remember 2 out of 3, so I passed the test. That's good. But
yeah, you. I think you addressed nearly all of them. I think. No, Andrea. Yeah. Yeah.
Okay.
So, about to be sure if I can actually insert it in the PhD line, my suspect would have been that you, Andrea, asked Tom why he used a complexity indicator different from the one you are using, because you in your thesis using Hidalgo, Hausmann, Barabasi, while Tom did not and rather opted for another complexity, which is based on structural diversity. And here actually there was one of my questions, if I can. I understood your concern about that measure of proximity, which I actually share to a certain extent. However, I ask and I wonder, to which extent you think your results will be somehow robust, if it's possible, to other complexity measurements? Do you think they would resist, or getting that spatial twist will change your results or not? Hard to say, but
I think it's an excellent question. Of course, whenever you propose a new measure, you're confronted with these type of things quite frequently, and I don't really have the perfect answer to that. The first one is, if I use another complexity measure as a kind of robustness check, I kind of admit that measure should work as well, and only if both measures result in the same type of findings, then I would say, well, my results are robust to the specification of the complexity measure. However, in the more likely scenario that the results will differ, then I don't know, is it because of my study or the empirical analysis I'm doing, or because of something which may not be optimal with respect to the alternative complexity measure. And the problem is with complexity, we don't have an absolute benchmark, an objective benchmark. If we would, we wouldn't need it, such different approaches. So what I do here, I refer back to the work I did in 2019, which is published in PLOS ONE. I said, well, we know certain things about complexity. Which measure reflects them at least to a higher degree than others? There is, however, the thing where I think one can argue that in this context, we should at least try Hidalgo-Hausmann, because we know Hidalgo-Hausmann is working for the US. It's also working for China. The reason being that the main argument of them is, of course, that there are certain mechanisms that lead to, or certain processes that lead to the co-agglomeration of complex activities. And they can work relatively freely, let's say, in the US as well as in China, because there are all sorts of factors, in particular, individuals are very mobile. So they can co-agglomerate if they have the necessary skills. What we do know, however, Hidalgo-Hausmann's approach doesn't work at all in Europe. So with European data, it fails. It fails greatly. And that's not only what I show in the paper, but even if you talk to Cesar himself and also to Pialix, it doesn't work. The reason is that we have, in contrast to the US, too many places that co-specialize in complex activities. Why is that? My thought is that basically because we still have these very strong national states. So if, for instance, Germany says, well, we're building a competence center in bioeconomy, and we locate it close to, I don't know, the chemistry industry or whatever, then another state will say, oh, we also need that, right? And then you have two places. While in the US, you would have definitely a convergence or at least a concentration process towards this one place. So that's at least my hunch. I really would like to test that. If anybody is interested in that, please approach me. But I think, therefore, it doesn't work in the European context. Other than that, it's a fantastic measure. So I'm not politically opposing it or whatever. I like it a lot. I think it can help us a lot in different circumstances. So just coming back, in our study, since we're focusing on the US, we could actually argue it probably we could use this measure as well. And I took a note down basically saying probably we should do that, because if not you, then a reviewer for sure will ask for it.
Yeah. It seems that this point has stimulated other questions, but if I can, then I'll leave the word to Francesco and Francesca, but because this is very much related to this issue of the complexity. Now, I got your point of selecting, Tom, the 271 technologies, right? Because you wanted to have comparable technologies. However, I'm wondering, to which extent this is imposing a sort of selection of the technologies you are observing. That is, I'm wondering, to which extent is the complexity of your technologies different among them? Is there sufficient variability, or maybe that by doing that, you are capturing technologies whose complexity, for example, is pretty similar, and you are ruling out other technologies' complexity, pretty different. So the very question is, might we have a sort of selection effect in pulling up these 200 technologies that might affect the generalizability of your results? And then I stop.
No, excellent question. And you're right on spot. But actually, it works in our favor. So actually, when you look at the evolution of complexity, which we have also done and work on another paper over time for the US over the long time period, you do see that the variance in complexity increases over time, meaning that the most complex technologies tend to be nowadays much more complex than the most simple ones than this was 100 or 150 years ago. So, and the interesting thing is that even if we now look at the smaller spread in complexity during those years, we still find something. So, of course, now you can say, well, that doesn't mean that we can generalize these findings to today's period, but at least from an empirical point of view, we could say, well, the variance will only increase over time. So most likely these patterns will become even clearer. However, we had our good reasons to focus on this early period, again, out of comparability. Also, the problem is with these patent data, there are not too many CPC classes that emerged recently. So most of these, even if we talk really modern things, they already are registered in the classification scheme in the 1840s. Sometimes it's absurd. So when you look at just going by IPC at the emergence, what was that, biotechnology? Well, the first patents appear something in 1870, and that is registered to that class. Okay, we know that's not really biotechnology from our understanding. So that's a challenge. The further we look to the more recent times, the less really new emerging classes or events we can really identify. And therefore we choose this early period where we have a good understanding of, this is where it emerged. This is how it diffused. Nowadays, everything's happening everywhere and we don't really see these events. So that's the trade-off. While definitely studying the more recent period would be more interesting, we have difficulties defining what is an adoption and what is really an invention. And there, just very quickly referring back to what I said before, I think we will have eventually to go to text data and see, for instance, the emergence of keywords or key concepts in patent documents. But we didn't do so in this study.
Thank you, Tom. Now I have in the line Francesco Lelli, Francesca Ghinami, and then Fernanda. Francesco, go ahead. We can't hear you. No, we can't hear you yet.
Can you hear me now?
Now we can.
Okay, sorry for for this issue. First of all, thanks, Tom, for the presentation. I have a question related to the role of asymmetric information for this kind of analysis, because you are considering a period where communication was pretty direct, was pretty in person, and obviously, if we consider some issues connected to information, the diffusion of information, because we are talking about diffusion and adoption, I think that the role of asymmetric information might affect in a strong way this kind of analysis. Thanks.
Good point, but I think that's precisely what we try to study, right? So in a sense, the diffusion pattern is a representation of the asymmetric information, because it means some place learns something, which some place inventor that it didn't know before, and that also other places at the same time don't know. So the diffusion pattern is really very much how you can say how information asymmetry is reduced in space, right? Because then you study whether this place knows now something the inventor knows, at least to a certain degree, and which other places may not know at the time. So I think the diffusion process can indeed be described as, at least with respect to this very particular technology, as a reduction process in information asymmetry. What you also might imply with that question is that, of course, some places had much better access to general information or to communication channels at a certain point in time, which we don't consider here in this study, but we're doing also another study where we, for instance, and there have been research on that looks, for instance, at the establishment of post offices during that time, because that meant there was a kind of steady line of communication, at least potentially, to a certain place. And that, of course, also explains some of these diffusion patterns. We don't do this here because I don't think it's, for this particular study, a primary driver, because the post office is also very much emerged in a kind of contagious pattern. So, right, they went step by step. With some deviations, but generally, so it wouldn't really change the story too much, but it's a good point, yes.
Thanks.
Right. I think that we can move up Fernanda, given that Francesca has already intervened. So Fernanda, then Francesca, and then I've seen that Andrea Scani has appeared. So Andrea, then we'll leave a word to him. Fernanda.
Okay, thank you so much, Sandro. Thanks, Tom, for your presentation. Just two quick questions. I know that normally Spaces data works pretty well with Europe. But normally in other parts of the world, having a patent is a very expensive, it's a very bureaucratic, cumbersome process. So I don't know if you have another kind of suggestions instead of patent data. And also, this is a bit related to what Andrea asked before. So we are in a pandemic where spatial proximity is not possible. So what are the implications of this? Yeah, and these are my two questions. Thank you.
Yeah, I think the first question is, of course, patent data has its flaws, right? And you're absolutely right. With this type of information, we most likely cannot make really generalizable insights or generate generalizable ideas for parts of the world where patenting has a totally different connotation to it, has a different social implication to it, and quite frequently is not possible at many times or even not even known. So absolutely, you're right. So as usual in our type of research, data availability introduces us to a certain type of bias, right? We are absolutely biased towards, let's say, the Northern Hemisphere and what we now consider the more developed countries. This is something I quite frequently miss in this type of debate, is that's not really by choice. So it's not like we're most interested in it. Most frequently, it is because of data availability. And I think here we have a lot of great approaches. CISA, for instance, Hidalgo collected now very interesting data on Brazil, which opens up that road. In China, we have now increasing access to patent data, for instance, but we don't really know what patent data represents in China in many cases. So there is some progress, but of course we should also be, and I can only encourage all PhD students to really look beyond patent data. Patent data is something for the old guys like Sandro and me. We're used to that. But nowadays you have, I think in particular, look at internet data, look at website data, which you can scrape today and get information in a manner that was unimaginable to us when we started our research career, so to speak. And if you acquire those skills, and probably many of you already have, working with this data, extracting this data, I think this will also allow us to look into places where we can't really look at with our methodology, no, not methodologies, not necessarily, but empirical approaches, and in particular the empirical data we're using. So I think this is really a call to all, let's say, starting researchers to really expand our literature, our knowledge away from patent data, which is great, which we can do a lot of stuff with it. But for a PhD, I would definitely say leave patent data aside unless Sandro is telling you to use it. And focus on other types of information that becomes available nowadays in a manner we couldn't have imagined before. The second question, just give me a hint.
It was about the role of spatial proximity nowadays in COVID times, something like that. Was it, Fernanda? Can I remember well? Or?
Yes, indeed. It was like, what if this is not relevant, no? Sorry, I'm in the open space, is about what if spatial proximity is not longer an issue, or it's not that it's no longer relevant, but it's not feasible right now.
But that's, of course, I mean, we can only speculate, but there are, there is, I've actually recently seen a paper, maybe you have that as well, because it's now circulated widely, that shows the effect on researchers' productivity due to, or that is related to meeting at conferences face to face. So actually, there they used basically this kind of setup we used to meet face to face in conferences. Then COVID prohibited rather us to meet face to face. Did it have an effect on our productivity? Of course, there are lots of issues in general that have to be considered, but the message is quite clear. We need we need interactions with each other face to face, and not virtual face to face, but really physical interaction, so to speak, because only that really allows us to not to really learn, but from my perspective, it is really about all the not only the nonverbal communication, which with video I think is also quite possible, but it's a spontaneous thing. I mean, about how many things you talk to your office neighbor, right, on a daily basis, from which new ideas may emerge, where you wouldn't, put on Zoom and randomly call somebody or Skype somebody with respect to that one. So it's this lower hurdle of accessing other people and talking to other people that allows for quicker diffusion of innovation, speed, and learning. And it is also this, you run into people randomly on conferences. You talk to people you never would have imagined to talk to at any point in time. So you learn from that. So I think those are two key mechanisms that we definitely lose or have lost for too long of time period during COVID. And for instance, I would love to be basically now not here, not only for the weather and the food, but really to have this closer interaction with you guys and go for a drink tonight, because then we would have to talk the real things and not just the content of this presentation, which is lost in this way. So we have to make sure that we get out of this because it has some implications. Of course, with this type of research, I can't show that, right? But at least the ideas, I think, become clear.
Thank you, Tom. Thank you very much. So Francesca, again, then we can open to everybody also to stuff. Okay, Francesca.
Thank you. Can you hear me again? Because
yes.
My computer doesn't work. Okay, thank you. So a quick question, maybe I missed it, but it seems you don't control for competition, both local competition and in the market, like sectoral competition. And these two types of competition do affect adoption or invention. So, and also you actually mentioned that more complex technology tend to arise in denser areas. So local competition would be important, but as well, like sectoral for the spatial distribution you want to analyze. Maybe you continue, I'm not sure.
No, it's an excellent point. Competition, we know, plays a huge role for innovation processes, right? I mean, this goes not only back to Porter, but I mean, has been shown also empirically quite a lot. We don't have it in here. And there are three reasons. First one is we don't really have good data, but that's a sorry excuse. So I mention it, but it's the second one is we're talking about the first adoption of a kind of product innovation, which patent data at that time in most cases represented, in a time when markets were not really fully nationalized, not even in the US. So meaning that at least for the time period we're looking at least for the first half of it, let's say between 1830 and probably all the way up to 1870, 80, we could rightfully argue that competition, at least in terms of the product market, was not really that essential, because there we talk really local markets to a certain degree. The third explanation is precisely what you mentioned too. Competition to a certain degree is captured by complexity. So our idea is for why complex or skills in complex technologies give you an economic advantage is because you have less competition, because it's more difficult to enter these areas, to obtain these expertise. More resources would have to be invested in order to learn these more complex technologies, meaning there's a much larger entry barrier. And at the same time, while there are potentially greater rewards, not everybody can stem this entry barrier, and these rewards are also there's a certain uncertainty about these rewards, so not everybody will do that. Meaning that one of the central mechanisms through which complexity unfolds its economic value is precisely by indicating here is lower competition, and that means I can, charge higher prices and extract a little bit monopoly or some kind of rents like that, stemming from lower competition. So we included that by means of these three ways. You can choose which one you like the best, but I definitely would say it would be interesting to actually compare that. So whether there is something to complexity in terms of generating economic benefits or translating into economic benefits, apart from this competition argument. Of course, there's more. You can always say, well, if you're able to do complex activities, you're always able to do simple ones as well. not sure about that. Think about all the scientists that are really good in specific fields, but when it comes to repairing a shovel at home or something like that, which is actually quite simple, may struggle. So this is, of course, a little bit more complex than that. But generally, the idea is if you're able to handle complex activities, you're able to handle simple ones, so you can work in those fields in principle, at least, as well. So that's an advantage. Also, it's easier for you to learn additional knowledge. So there are other advantages than the competition argument when it comes to complexity. I don't know of any study. If anybody knows anything, please correct me. I don't know of any study that really disentangles that yet. So all we know is complexity pays.
Thank you, Tom. Thank you very much. So we can now open also the floor. I mean, it is basically open. We have another 10 minutes or so, no, 15 minutes. Andrea, please go ahead.
Thank you, Sandro. Hi, Tom. It's great to have you here. Thanks very much for the talk. Super interesting. I had a question more for future research stemming from what you spoke about and what you presented. I missed the first minute, so maybe I'm wrong and you mentioned it. But I would like to have your take on what you think about the importance of integrating and understanding into these studies on technology diffusion of the underlying geography of firms, because I guess firms are the organizations where most patents are produced, right? So is it an important thing, understanding their linkages and their behavior and how they organize activities in space to understand technology diffusion? For instance, the large jump mode of diffusion that you showed might be consistent also, especially in a context of localized markets that are fragmented in space, can be consistent with a multi-plant firm that invests somewhere else. And that patent that we observe happens within the same organization. Or even the contagious mode of diffusion that evokes technology diffusion as a cloud can be actually consistent with a very localized network of companies. So how do you think we can integrate the geography of firms, of organizations into these studies of diffusion?
Excellent question, and hi, Andrea, by the way. I will respond to all your emails quite soon. Sorry, I was teaching intensively with us. Coming to your question. Obviously, it's a very important dimension. But let me start first by saying, for the time period we're looking at, I don't think it is as important as it would be for nowadays. Because what I mentioned before, at least for the largest part of the time period we're studying, invention processes were not organized in a kind of firm level R&D lab, R&D department type of way, which we're used to today. That emerged later. And that also meant that at that time that we're studying, it really boils down to the inventor. And there I would say it's probably would be more interesting to incorporate inventor mobility into the pattern. Which we haven't done so because for this data, it's really difficult to get that, but it's not impossible. So I know Ernesto and so on, they work on these type of things. So that's, of course, a dimension where we're blind here in this study, which definitely explains some of our results. I'm sure of that. But we also know, of course, that this inventor mobility most likely will not reflect this contagious diffusion. Because who would move from New York to the suburbs to do innovation, let's say very roughly, or to the local periphery. So there we would probably have in particular this east-west diffusion pattern being subject to that one. Speculative at the moment, but my hunch is there should be something. What you actually said to is looking, or what you referred to is looking at the organization of production and distribution, not only production, but also distribution offices over time by companies, which I think is absolutely vital and has has been considered also in the early studies of innovation diffusion. So when you look at Rogers and Hagerstrand and so on, which looked at really products. And there they, of course, looked at also distribution offices. So whether you had a salesperson in the region that was actually selling your product. In early days, of course, you had these salesmen, women traveling around, which of course had a huge impact on the distribution. So I think that would be interesting to look at. But coming to your, if we talk more recently, if we would study the same phenomenons these days, then of course, I mean, you're involved in that as well. The work of Kerstin, for instance, Schaefer is really crucial, where you see companies entering certain locations to not only have access to technological expertise, and thereby potentially benefiting from diffusion processes earlier, but also for political reasons and for other types of access reasons to certain resources and processes. So, well, the nice thing is about this is all quite complex, and there's so much to be explored that we're not going to run out of work here. So that's the good news. But definitely the firm dimension generally, yeah, at this stage, probably less so.
Okay, Tom, are you happy, Andrea? You want to follow up on that, or are you happy?
No, thank you very much.
Okay. So actually, the issue of the mobility of inventors was actually one of my questions, because what I miss in the story about diffusion, when you measure that way, is somehow the connection between the first inventors and the next inventors somewhere else. And mobility inventors might be something to fill that gap, but there's another mechanism you didn't mention, and I was wondering to which extent it could have a role, which is citations of these patents. And any way to use patent citations to fill somehow the gap between the original and subsequent inventions in terms of knowledge spreading. I didn't see that Ugo also was raised. Sorry, Ugo, I'll leave you a word afterwards. Sorry.
No worries. Thanks.
We leave Tom answer to me, and then we let you ask. Okay.
Okay.
But I will be very quick on some though. So so the answer is patent citations, awesome if they would be available. At least not for that time period. We did another study with Marcel as well, who I didn't mention explicitly as a co-author. I should have, sorry, a former PhD student of mine, where we tried to explain patent citation patterns in space, in that case in Germany, and looking at whether policy projects or supported projects had an influence on that one. And that turned out we don't really find that strong of an association. So patent citations you can study. They are not, please correct me anyone if I'm mistaken, but I'm not aware of it, that they are available for such a long time period. So other than that, yeah, we would definitely include it. I think David Rigby is working with this until I think all the way back to the 70s. Somewhere there is the breaking point. So some data is available, but not all. The same is true for inventors. So we, that is Marcel and me in this case, we cannot identify inventors in this type of patent data because that database is not available. But I know that the guys surrounding David Rigby and Pierre Alex, and in particular Frank van der Wouden, who's I think now in Hong Kong, they have used text mining processes to identify inventor names in this database. And Frank has published a couple of papers using that also over a long period of time. It only works for subsample of patents. If I remember correctly, something like 40–50% of the patents you can identify inventors in there, not without problems, of course. So you can do some stuff. But when it comes to the diffusion, where we really would like to capture at least the entire knowledge, then as usual, we have trade-offs. And I think then looking just at 40% of the patents might introduce a very substantial bias that may outweigh the benefits. But definitely future research, if it has access to these type of data, go for it, right?
I didn't know, frankly speaking, that citations data were not available. Well, in terms of inventors, I'm wondering whether recent paper by Andrea Morrison and someone else on economic geography goes that back in time, or I don't know.
Yeah, so that's the group that I mentioned. So that's
the group, yeah, okay.
So Sergio Petrella, who
yeah,
that database. and Frank van der Wouden,
is
they
that group?
were the ones doing most of this text mining, and they have some access to this data. And although I know them very well, they haven't given me the access yet. So,
oh, that's bad. Okay, so let us conclude with the very last question. I mean, we have exhausted our time available, so which is good. I mean, we had a lot of discussion. Ugo, please go ahead.
Hi, Tom. Thanks for your excellent talk. My question is regarding innovation and its spread. I wonder if, in addition to concepts which imply a more horizontal view of the diffusion, like contagion and the like, if we might integrate our lexicon, our vocabulary, also with the terms and notions like predation, extraction, because of the configuration of today's capitalism, which is based on this power of high-tech corporations, which are predatory, predatory entities. The extra-legal dimension of this high-tech corporation is today widely debated across the world, especially in the United States. Capitalism, according to many economic commentators, they are reminiscent of a kind of monopolistic capitalism of the 20s in the last century. So I wonder how this predatory extractivist dimension of today's capitalism is reflected in your idea of the geographical spread of innovation. If it is present. Yeah, thanks.
Yeah, I think it's a very interesting debate it actually alludes to. And of course, you followed that one right now also in the press is about the vaccination or patents on vaccinations, for instance, right? So a patent by construction grants a monopoly. I mean, that's a very basis. And of course, we thereby exclude certain people, and usually not the wealthy, let's say, certain people or regions, countries, whatever you want to name there, from at least using and commercializing this particular type of invention. So in a way, you could also interpret this study as the emergence of at least temporary monopolies, right? So, which is, of course, a quite unusual look at patents, but it is correct. I think what I like about the patent mechanism is that, firstly, it doesn't prevent you, a patent doesn't prevent you actually from using a certain product or process and learning about it. It just prevents the commercialization of it. So while the economic side and the commercial side has, of course, some serious implications, at least some of the things can be done with it, and some of the benefits of these innovations can still come to other places or to other social groups that, at least from the commercial point of view, might be excluded from it. And this is, I think, this debate that is also reflected in this paper. The nice thing about patents in that case is they open up knowledge, because not only do you pay a patent fee for something, but at the same time, you also have to make your knowledge public. Everybody can see what you've put into the patent. Of course, there are certain ways you could try to hide what's actually behind it. So actually, I think in this study, it really reflects quite well what type of knowledge is made public in a certain place at a certain time, and thereby becomes available to others. And I think that's, at least from my perspective, the positive side to this type of system that is very much about securing the returns on intellectual capital, which have a lot of negative sides. I didn't refer you to the recent debate on where is it now? The dark side of innovation, of course, right? So not all innovations are good per se. And of course, also to, again, this access to knowledge, to what you can learn from it, which is a positive side. But on the other hand, as you mentioned correctly, in a sense, the patent represents a way of extracting economic rents from intellectual property. And as we know, in particular, from some of the patent wars and things that have gone on, not everybody who does a patent is actually the inventor, right? So this is also somebody else is just better in patenting or quicker or has the means to do so, that gets then all the benefits of it, even though this person might not have been the original inventor. So these are some dimensions that relate to your debate that I think relate also to the study I presented here. But of course, we could debate this far longer. There's many more aspects.
We're gonna do that when you will come here, possibly soon in presence, because I think that we need to stop now. It's 12 o'clock. So I'm afraid that even if there are more questions, we can't take it anymore. But again, I think it was great, Tom. We really thank you a lot for this super interesting paper, and above most for having so extensively addressed all the questions that you received, which were so heterogeneous, so sparse, not sometimes very much related to the paper, but I mean, we really benefit from the discussion that you provided to us in each and every respect. So we are very, really grateful to you for this effort. Having said that, again, we look forward to having you in presence. I forgot to send you regards on behalf of Alessandra Fajan, who unfortunately couldn't be here because she had a surgery some time ago. She's just recovering, but she was not really well enough to stay here. But she dropped me a line, send to my warm regards. So I've done that. And having said that, yeah, to all the attendees, I've just reminded which are the next webinars. Tom, if you are interested in the next webinars, they are available on our website. So if you want to participate or even spread the info, please do it, okay?
I will definitely diffuse it. And let me, before you finish, I really want to thank you all for the attendance, but also for the questions. And I'm absolutely amazed. I mean, I've been to a lot of research seminars, and not always do I get that many and that excellent questions. So this really speaks to your group. So thanks a lot. It was a pleasure on my side. It's fantastic. I will come back.
We will definitely need to arrange a visit in presence soon, okay? Let us work on that and stay in touch for that and for other reasons, of course. Thank you very much, Tom. Have a good day, and ciao to everybody. Thank you very much. Ciao, ciao.
Thanks a lot. Bye-bye.
Bye.